This is 6.2.3.1. We are going to apply the DTFT and DTFS on a periodic sinusoid. So the sinusoid that we are going to examine is this. It is a cosine with angular frequency pi over 4 and with a phase shift of minus pi over 2. To analyze DTFS, the first thing that we have to establish is the number of samples per cycle for this particular cosine. Since the angular frequency is pi over 4, it will take 8 samples to make 2 pi. So we find that capital N is equals to 8. Now typically if you want to calculate CK, you have to do it in this way. You would find the sinusoid xn for n equals to 0 to 7, plug it into this equation over here, and changing different k's and different n, you will calculate and compute CKs for k equals to 0 to 7 in this example. But there's another trick. We know that we can decompose cosine using the Euler identity into complex exponential. So the cosine actually is this equation over here. A cosine pi over 4n minus pi over 2 is exactly EJ pi over 4n minus pi over 2 plus E minus bracket pi over 4n minus pi over 2 times A over 2. So this is the amplitude A of the original sequence divided by 2 because it is being distributed for these two complex exponential. Now actually when the sinusoid is in this form, it is very close to the synthesis equation, and in the synthesis equation it will reveal the CKs. So that is the strategy that we are going to use. We are going to convert this form into the synthesis equation, which is this guy. And once we have mapped this synthesis equation to this form, we can identify the CKs by inspection directly. Why do I say that this equation and the synthesis equation looks the same? Well, what you need to do is that you have to bring the A to E positive pi over 4n, and you break this minus pi over 2, the phase shift, out. You bring first the phase shift outside. So this becomes CK. The question is, which CK is this? This K equals to what? And to identify that, we have to identify which frequencies they are in. You notice that one of them is at a positive frequency pi over 4, and the other one is at a negative frequency minus pi over 4. You look at the synthesis equation. We are using k equals to 0 to k plus 1 for only positive frequencies. So later on you'll realize that the negative frequencies that we see is simply at the higher ranges of k equals to 0 to n minus 1. Now we have to find out which k is it. Let's examine for the positive frequencies. Remember that the number of sample is 8, so n is equals to 8. So this is pi over 4. So in fact, if this is the fundamental frequency, omega naught, therefore omega naught times k equals to 1 is the CK. So this particular k is actually C1. And what about this? This would be C minus 1 because he is at the minus the pi over 4 frequency. Now CK equals to minus 1 is the same as C7, because remember that the CKs are n periodic, n sample periodic. So C0 to C7, C8 to C15. So we use the trick of inspection of the synthesis equation to the Euler decomposition of the complex exponential and we identify C1 and C minus 1. Now we are going to plot. So let us plot with respect to K, and K at 1 will have an amplitude of A over 2, which is over here. So this guy is this guy. And it would have a phase shift of minus pi over 2. So this guy is this guy. The frequency, the phase shift is minus pi over 2. Now, I also plot with respect to omega. Omega is the angular frequency. The angular frequency is at pi over 4. So, where k equals 1 is pi over 4. So this is the value that I'm talking about. So k equals 1 is mapping to the angular frequency pi over 4. Now what about the k equals minus 1? So we swing to the left hand side, but this is the negative frequency. So it's at minus pi over 4, or it is the same. We should call it at k equals to minus 1. And we have the same amplitude, A over 2. However, the phase is plus pi over 2. Alright, so this is the DTFS representation of CK in the equation as well as in the graphical representation. This is the magnitude plot and this is the phase plot. So once we have this, then what do we get? And how do we get the DTFT of this? What we do is that we are going to take this exact figure and then change it a little bit. And how do we change? The previous slide has told us that we must multiply the CK by 2 pi and we must introduce the delta function. So 2 pi times A over 2 becomes A over A times pi. So the amplitude now is A times pi. And now we have a delta function at this particular frequency, and the delta function means that it is an arrow sticking at this frequency. So this is the magnitude, and that is for the positive magnitude. So the positive magnitude is A pi now. What about the phase? Minus pi over 2. So this is still minus pi over 2 at this particular frequency, represented by a delta function at omega. Similarly, for the negative frequency, because this is omega equals to minus pi over 4. So omega is now minus pi over 4. The amplitude is A over 2 times 2 pi is A pi as well. So this is A pi. And the phase is plus pi over 2. So this is pi over 2 at the frequency minus pi over 4. So to convert a DTFS to a DTFT, a representation graphically, you are doing it this way, and for equation representation, you are simply multiplying by 2 pi and introducing the delta function at that particular frequency. On the left, we're using x omega represented by here with the synthesis equation, and we realize that we are simply using the delta function and the shifting property to multiply by e plus j omega n to introduce the omega at the omega naught, which is in our example pi over 4. This then brings us back to the Euler representation exactly of the cosine. Thank you.